this is what we're talking about. The main topic is approximations of functions, functions with functions. Okay, so the problem we started with was to approximate what was it, square root of 4.1. One number at a time, but really what's behind it is to approximate the whole function at once. But at the same time, we are approximating it only in the vicinity of one given point, as that circle indicates, because you can see as we move away from that point, it's not gonna look good. As you can see that our approximation has become unacceptably bad. So this is what I have here. That this indicates the difference. This is the error. Let me put it this way, yellow. The error between what? The function that we approximate is this. This is my f. It is in fact cosine, and I'm trying to approximate it with a different degree of quality of functions with and degrees are here. This is 0 and 1. Okay, that is the constant and linear approximation of that blue function. Okay, so both of them are linear, and just one of them is constant, and just happens to be horizontal. And then secondly, we have over here I have 2 and 3. That is, as you can see, there's a parabola, and it approximates better our blue curve. And finally, we have here this is degree 4 and 5. Okay. So that approximates even better, and the degree, the range at which the approximation is acceptable expands more to the sides, but it's still look at the possible errors. Eventually, as you move away from that point, the point that I marked in the middle, the things will become bad. As you can see, it is after all, what is that orange curve? It is actually a 4th degree polynomial, and 4th degree polynomial, what is so special about polynomials in general, and that's the biggest problem of this we're going to face, is that they go to infinity. Okay, so either go down to infinity or plus to infinity, but they do. Okay, that's what we know about polynomials. And that if we're talking about approximating cosine, it does not go to infinity, which means that the gap between the two functions will eventually become infinite, and so that is the limitation of the method. But it is best we can do, at least in the vicinity of that point in black, the origin. It will be the approximation will be good, or rather, it will be getting better and better. So the way we have approached it is the sequence of events. Constant approximation, linear approximation, quadratic approximation, and then what we have noticed is that the best approximations are, it actually makes perfect sense, that they share derivatives with the function. Okay, so once again, if we're talking about approximating function at a point, okay, or rather in the vicinity of a point, how can we get approximated better and better? And the answer is, well, have more and more derivatives equal to those of the original. Okay, so that's exactly what happened. Constant function is no derivative, linear function 1 derivative, quadratic is 2 derivatives, and so on. You'll have more and more derivatives that coincide. Okay, so this is the examples. We'll keep coming back to these, how to compute approximations of functions given by some formulas that cannot be computed by hand. And we turned out we can do it by differentiation. So that's another example of cosine, the illustration we just saw, and we got constant and linear approximations of that function, and quadratic too. So that orange, the green curve over here is this one. Okay, quadratic approximation, and you can also see the 4th degree approximation as well. Okay, now we're trying to build a bigger theory for this, and the approximations will be with polynomials. So polynomials are the simplest functions that we can handle. They are easy to compute, direct. So you don't need any extra computation, no division, no sine, cosine, nothing like that, exponential, nothing like that. Polynomials are computed by what? Addition and multiplication, period. And those can be done by hand, and the computer will do it easily as well. So we start with reviewing polynomials, and that's step number one over there, is to progress from just polynomials as we know them, the line over there, to polynomials centered at a particular point. So centered at a point, a new polynomial which looks exactly the same, except it has, instead of having repeated terms x squared, x nth power, we have x minus a repeated, and then up to nth power. Okay, so the same polynomial, it looks different, but it could be the same polynomial, can take that form or this form. You can go back and forth as necessary. At this point, we'll just assume that it can be done. Okay, so suppose we have a polynomial of this kind, and we'll just see what happens. So what we can do with it to begin with. And number one step is just to figure out what the derivatives are. Okay, so and that's what we got. I'll go over this one more time. The last step is just I want to refresh your memory of what a factorial is. So or the factorial rather. The factorial is a sequence. Well, is this sequence given recursively? So A1 is equal to 1, and then you just keep multiplying it. So A2 is equal to 2, A3 is equal to 2 times 3, A4 is equal to 2 times 3 times 4, and on and on. So recursively then an plus 1 is equal to an multiplied by n plus 1. Okay, so just keep multiplying it by larger and larger numbers. So that dot is why we have to say that the definition of that's why the sequence is recursive rather than it's not really an explicit formula. You cannot compute this the factorial without going through all the steps that precede it. So that's why that's why I prefer to think of it as a recursive sequence, and that's what we're gonna face anyway. Everything from now on sequences will be for the most part recursive. So that is the factorials. It's a sequence. It is growing really fast, by the way. So it in fact, if you want to compare it to other sequences that we have seen, and the sequences that we have seen were a while ago. Remember, they were the two main ones were arithmetic and geometric. Arithmetic was both of them given by recursively. So it is arithmetic. It is an. Well, let's use b. Bn plus 1 is equal to b plus, say, bbn plus p. So every time you progress, you add a number. Okay, so that's arithmetic progression. Like you deposit an amount of money every time. And geometric, you multiply. Same idea, but you multiply by the same number, on and on. Okay, so these are three examples of recursive sequences, and you can notice that now you can see, especially if you look at the last formula, compare the first and the last, you can see how it grows. The factorial should be growing faster because you don't multiply by the same number as what geometric sequence is. Geometric, by the way, also known as exponential growth. Okay, so if you speak of it informally, you would say, well, it is fast growth, exponential growth. But factorial grows faster because you multiply by a number, larger and larger number at a time, not by the same number. When it is a big number, you multiply by 10, by 10, by 10. It grows faster, but if you multiply by numbers that actually also grows, that will grow faster. Eventually, it will overcome the geometric progression as well. So that's the factorial for you. Hardly can have anything faster than that. And now, where does it come from? Not typically. So these two can be thought of either once again bank deposit, bank account, and you deposit the same amount at a time, every unit of time, so that's arithmetic. If you have compounded interest, that would be geometric. But where does the loss comes from? The new one, the factorial, and it turns out it's really the one example that we already saw. It is the derivative. That's where derivatives come from. So, for example, if I start with the power functions. If I differentiate, say, x cubed, if I differentiate enough times, what do I get? So if I differentiate it once, I'll have 3x squared. If I differentiate one more time, it will be 3 times 2x. And I differentiate one more time, what I end up with is in fact 3 factorial. Okay, so that applies to any other examples that we saw last time. I could actually start with the nth derivative, or rather nth power, and if I start differentiating, I eventually will end up with a factorial, n factorial. So I differentiated n times, so as xn. If I differentiate it once, I will have, let me just write a sequence, n xn minus 1. I differentiate one more time, it will be n minus 1. It doesn't fit. Then I progress on to n minus 1, x n minus 2. Okay, and then I keep going. I differentiate one more time, n minus 1, n minus 2, x n minus 3. Okay, and the degree goes down, 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 and until in the end of, if I do it n times, I will end up with n minus 1, n minus 2, all the way through, and then it will be 3 times 2 times 1. In other words, it is n factorial. Okay, so in other words, it is the nth derivative of the nth power function. Okay, just n differentiation gives you n factorial. You can see how those things, the powers drop down as coefficients, and eventually you will end up with all of them listed, and that you have your factorial. So this is also in fact recursive. So all the differentiation, how do you get nth derivative? You cannot get the nth derivative directly. You have to go through all the steps. So differentiation is recursive as well. So it produces, gives us a sequence of numbers, and it doesn't really matter over here whether it is xn, or I could start the same way, x minus an, and I have the same sequence. Differentiation, that minus a part doesn't really make any difference, and once again, after n differentiation, I'll have still n factorial. Okay, so one at a time, derivative by the chain rule, x minus a, derivative is 1, so it's gone. And I still have n factorial. In fact, furthermore, if I take my polynomial and I have a bunch of terms, I have polynomials centered at a, so the first term will be xa minus, well, say cn, xn minus n. Okay, so that's my polynomial centered at 0. And then there is a bunch of terms. It ends with c naught. It did, in fact, the whole polynomials is there. Okay, so what happens if I differentiate it n times? A polynomial of degree n is differentiated n times. What happens? Now, what happens to that this term? What happens to this term after one differentiation? It goes to 0. After just one differentiation, it's gone. Okay, so this goes to 0. If you have a linear term, the linear term is say c1 x minus a. Well, it will take only 2 differentiations. It will take 2 differentiations to get it to 0, but you still have that, and you have 0. If you get the next term, which has the power of 2, it will take 3 differentiations to kill. The 4th degree will take 4 differentiations, and so on. So if you have n terms and n differentiations, then all of them will die except for the very first one. So this will be all gone. After n differentiation, the lower degree terms will be gone. Okay, and you will be left with the same differentiation we just saw right above, or on the left, on the right. There will be, once again, Cn n factorial. So Cn is just a coefficient, and the differentiation of a power function of degree n will give you n factorial. Okay, so that's the thing about this, and but I want to have the general picture. So let's I need all derivatives, in fact. So that's the very last derivative of the nth degree polynomial. The rest of them are zeros. But what about before that? Okay, before that. So there it actually will have after one differentiation, two differentiation, three differentiation. So let's look at this one more time from the beginning. So my polynomial is, so p of x centered at a is which one I want to, yeah, okay, c naught plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed, and the last one is cn x minus a n. Okay, so and then I'm not going to be looking at the derivative, just the derivative. I want to find the values of all of its derivatives at a. Remember, that is our goal, not derivative as a whole, but just at a, because that's where we're going to try to approximate. We try to match our polynomial with the function. There's no function yet, but that's the plan, to match it with the derivative of some function that is being approximated. So we cannot just look at the last derivative. We have to have all the derivatives matched. Okay, all the derivatives, including the value that we're starting with. So so let's just compute. So p of a is, starting with degree 0. P of a is in fact c naught. Look what's happening. I just plugged in x equal to a into my formula, and all the terms disappear. Right. And so, so then I know that's the value I'm going to be matching with my with that function that's still to come. Then now I differentiate. P prime of x is equal to c naught plus c naught is gone. I'm sorry. C naught is gone, so I have 0 plus c1. The second term turns into c2 x minus a plus c3 x minus. I'm sorry, I missed the terms. Okay, so I'm differentiating in this manner. So it will be c2 2 x minus a. Okay, plus what's the next term? Second power, okay. And the last one is cn x minus a n minus 1. Okay, so let's look at all of them at the same time. But now, well, let's compute them first. Let's compute the first. So the second derivative will be 0 plus c2 times 2 plus c3 times 3 times 2, x minus a is still there, and on and on. The next one is c n minus 1, x n minus 2. Okay, so the coefficients growing. We have seen already this happening, and how the factorial starts to form. But this is just the beginning. Let me do one more derivative. The third derivative is 0 plus c3 times 3 times 2 plus all of these, and I have cn n minus 1, n minus 2, and it does not fit, x times power n minus 3. Okay, so the nth derivative is, well, we already know that these all will be zeros, and there will be only one last term. We already know the answer. It is cn times n factorial. Okay, So, so that was a preliminary computation, because now I only care about the values of these functions at not at 0. I'm sorry, at a. A is our interest. X equal a is the point of interest. Everything is centered at x equal a. Okay. Okay. So let's go backwards like this, and let's just write up all of those numbers. We're creating a new sequence, as a matter of fact, a new sequence of numbers. So this is a sequence of functions, but we're gonna now do a sequence of numbers. In fact, let me mention that Pn plus 1 and anything beyond is equal to 0. Okay, so we don't care about what's happening beyond nth derivative. So this is P of a, once again, is equal to C naught. P prime of a is equal to, what is it? P prime of a, look at it. Wherever we have x minus y present, x minus a present, will disappear when we plug in x equal a. Okay, so we're left with C1. Okay, now similarly, x minus a is still x minus a is gone. Okay, x minus a, once again, wherever it is present, it will be gone. So I'm getting P double prime of a is equal to 2C2. Okay, so not the same. It is not just the coefficient, but coefficient with an extra multiple. Okay, the next line for P triple prime a, and as you can see, once again, all of these terms will be gone, because we have what we have present here is x minus a, and x minus a turns into 0. I'm sorry, this is x minus a everywhere. Okay, so so the answer is then 2 times 3 C3. And then we continue on. The last one we already did. So the nth derivative at a is the same. It's once again C n factorial. So all of these are in fact factorials. If it is not quite clear that this is 2 factorial, this is 3 factorial, the next one will be 4 factorial, and the n is n factorial. Okay, this is 1, which is 1 factorial, if you prefer, and probably if you want a 1 formula, then it all fits, and that is why, by the way, 0 factorial is equal to 1, or even though it doesn't make sense, but you cannot multiply 0 times by itself. But just to create a 1 formula that fits all, you start with 0 factorial is equal to 1. As you can see, everything fits. So the formula then becomes what? P sub k, the k derivative of p at a is equal to k factorial ck for k running from 0 to n. Okay, so that's our theorem that we have proven. So once again, the polynomial that it is a part of the theorem is the polynomial given by this. So we have a polynomial centered at a, and if we differentiate, we can actually differentiate all the way through and find all of its derivative, all of its derivatives that we care about. Beyond a and a, they're all zeros as well. So there you go. Differentiated once and for all, and so that will be helpful. Okay, so. K factorial, ck, all of the coefficients will reappear, but k factorial is 2. Okay, so so now let's try to, based on this theorem, let's try to follow that program that I have indicated as our a long-term goal. So given a function f, And I suppose we only suppose about it one thing. It is n times continuously differentiable. Continuously differentiable means that its derivative is continuous. And not everywhere, but just at one point. At that point, that the only we care about. Okay? Then what we are going to be studying is Taylor, what's called Taylor polynomials and Taylor series. And this is a Taylor polynomial will satisfy that property. Then the Taylor polynomial of f at a is given by, so Taylor polynomial will have a match of the derivatives. Well, a Taylor polynomial t sub n. I'm sorry. The nth degree Taylor polynomial. So once again, the idea is that we already have three that we have looked at: the constant polynomial, degree 0; the linear polynomial, degree 1; the cubic, the quadratic is degree 2 Taylor polynomial, and we want to have all of them just in case, because we don't know ahead of time what kind of accuracy we might need. So we want all of the degrees. So nth degree polynomial, it has the same. Let's use words rather than be specific and say what it is. Let's just put a requirement here. Is a polynomial all derivatives of which at x equal a are equal to the ones of f. So p, k, well, let's use t here. T sub n k at a is equal to f prime, f nth derivative, kth derivative at a. Okay, k from 0 to n. Okay, so that is the definition. A polynomial that shares of the derivative up to n with the original function. That's the one that we want to approximate. Okay, so once again, I could even write it out. Well, let's first use the theorem to actually be specific about what that polynomial is. So that's a theorem. We can actually write out what the coefficients are, right? So okay, let me just derive the conclusion based on the definition and the theorem and definition put together. We know what derivative is supposed to be. Taylor polynomial is a polynomial centered at a to begin with. Okay, and then its derivative is known, right, in the theorem. So we just write what we've got. So k factorial is c sub k is equal to f k derivative at a. So what the kth coefficient c sub k of t sub n is from this equation f k derivative at a divided by k factorial. Once again, k runs from 0 to n, and if you just start plugging in things, you can see how it happens, and we just can just recover what we have done so far. Well, let me quickly run through that example that we had. of cosine, so f of x is equal to cosine x. It is certainly infinitely many times differentiable, so everything is fine. F prime of x is equal to negative sine x. F double prime of x is equal to negative cosine x. F triple prime of x is equal, you can do, once you have the formula figured out, it's really no trouble to find your approximation at any way you like. So after 3 differentiations, we'll have sine x. Okay, and so let's say this is sufficient. Now let's do one more. Why not? 4th derivative of x is equal to cosine x. Okay, so now we evaluate the derivative at x equal, let's say 0. So f of 0 is equal to 1, f prime of 0 is equal to 0, f double prime of 0 is equal to negative 1, f triple prime of 0 is equal to 0, f 4th derivative of 0 is equal to 1. Okay, and now finally I'm writing the coefficients. C 0 is equal to, according to that formula, so these are the k's. K 0, 1, 2, 3, and 4. Okay, and so I have my function in the first column, the second column, I'm sorry, the function is derivative in the first column. In the next column, I evaluate that function at 0. That is our A is 0, and then now I'm evaluating the coefficients. So I don't have the formula yet, but the coefficients will be, what I'm supposed to do, I take that, well, I have computed the numerators, right? Look at it. I have the numerators in that last column, so I just have to divide by k factorial. Okay, so k factorial will be then 1, so it will be 1. Then, well, let's just write it out. I think I'll just write it like this. Okay, then C1 is equal to this number that we have divided by 1 factorial. So it is 0. C2 is negative 1 divided by 2 factorial, which is negative 1/2. Right? Okay, C3 is 0 divided by 3 factorial, which is 0. C4 is equal to, what is it? 1 divided by 4 factorial, which is, what's 4 factorial? 24. Okay, so these are the coefficients, and so we did up to 4. Does it mean that we found only one Taylor polynomial? No, we actually found 5 Taylor polynomials, because for each degree lower than 4, now we can create a Taylor polynomial, because they expand one term at a time. So we can take as many terms as we need in order to approximate as well as we need. So once again, this is, how should I put it? This is constant. The constant, or T0, degree polynomial. Then if I combine these two together, this will be the linear, T1, and on, this will be cubic, quadratic, I'm sorry, quadratic T2, and one more. This is, if I go all the way this way, it will be cubic, T3, and then the last one will be T4. But how many terms it's supposed to have? It is n degree polynomial will have n plus 1 terms, so cubic will have 4 terms. Okay, so these are the coefficients that you see above, all will be played. So let me just write it out, the data that we have. So T0 is, that's the easiest one, T0 of x is simply equal to 1. Once again, this is my picture. The red one is 1. The second one is T1 is of x is, according to my formula, it will be 1. I am recycling the previous term and add the new term, linear term. So it will be the coefficient we found, it is 0 times x minus 0. Okay, so as you can see, the coefficient is 0. That's why there is no extra term. There is no extra term, which is still equal to 1. And that is why the red line has two markings, 0 and 1, because it's simultaneously the constant and the linear approximation of our function. Okay, so further than a quadratic, I'm moving to T2. Once again, I am recycling the first two terms. Okay, so I still have these, and I add one more term, which is coefficient is negative 1/2 x minus 0 squared. Okay, in other words, it is 1 minus x squared over 2, which happens to be, well, it happens to be in green here. So this is the one I'm talking about right now. Okay, a quadratic polynomial pointing opening down. Okay, so you certainly can confirm that it passes through the origin, and then it branches are expanding down. The cubic one, T3, once again I am recycling the first three terms, 0x minus 0 plus negative 1/2 x minus 0, and then one more term. The coefficient is 0, x minus 0 cubed, and then turns out that there is no difference. Once again, we're adding a term which has no coefficient, 0 coefficient, which means that we're not adding anything, so it's the same polynomial. So cubic is the same as quadratic. Let's do one more, so to justify that picture. The brown curve. Alright, so I'll do one more term. Okay, T4 of x is, once again, I will repeat this. That is easy to write, so writing is easy. Cubed, and the fourth is the coefficient is 1/24, 1 over 24, x minus 0 fourth power. Okay, so then the answer is finally will be 1 minus x squared over 2 plus 1/24 x to the fourth power. So as you can see, adding the last term, even though it's a small term, you divide by 24, but it actually reverses the branches. Instead of for the second degree, it was pointing down like this, right? That quadratic polynomial, but negative x, or x squared over 2. But we have now positive x to the fourth, which means that's why the branch is now pointing up. See, this is what happened between the green and the brown. They match very nicely in the middle, but on the sides they actually will go towards two other infinities. One goes to negative infinity, the other goes to positive infinity. Okay, so that is the approximation. That's how Taylor approximations work. Some of the computations are simpler than others, so let me maybe do one more example. Yeah, let's do one more example. So that's the formula. I prefer, the whole idea is recursive, so this is all recursive. So don't try to jump straight to the polynomial that you're interested in. You're interested in the fifth degree polynomial, don't go straight to 50. You will have to go through all the steps. You will need the derivatives, all the derivatives in between, all the, so you'll have just as well go through this plan. A table, and then you expand down to, up until you're done. Okay, so in fact, sometimes it is in fact possible to go all the way. This one, all the way, what do I mean all the way? It means you can find simultaneously all the Taylor polynomials. All the Taylor polynomials that exist here. You can see that it is not entirely predictable. I mean, the pattern is unclear yet. So if I keep differentiating in that manner, so even though I know what the factorial, how it will appear, but how the derivatives will behave is not entirely clear. So we're differentiating cosine repeatedly, infinitely many times. What is it going to produce as a sequence? It takes some thinking, but there is one function that has exactly predictable derivatives. So what is the function, the derivative of which we know all of them simultaneously at the same time? What is the function that is easiest to differentiate? Function that is easiest to differentiate. N times. I mean, all of them are easy to differentiate if you once, because if you know the answer. But there's one that is really easy. E to the x, right? Because it's its own derivative. So you differentiate, nothing changes. All right, so e to the x, you differentiate, e to the x, you differentiate it, e to the x, and then on and on and on. It will be e to the x all forever. Okay, so maybe that's why we like it so much. That's why it was picked among all the exponential functions. This was picked because it has such a easy derivative to compute, even though it's certainly not a polynomial, right? So it has its complexity elsewhere, but not with differentiation or integration for that matter. So if we have all the derivatives available, so let's go through this plan once again, but with this simpler function. Okay, so we still have, I put case here, so 0, 1, 2, and the pattern will appear very, very clearly, easily. So I'll have case derivative here, so e to the x, e to the x, e to the x. After n differentiation, I still have an e to the x. Okay, then let's still center at 0. So xa equals 0. Okay, so then I have fk at 0. So it will be, once again, the derivative doesn't change, so y, that's not going to change either. 1, 1, 1, 1. Okay, so there is no change in the derivatives, in the values of the derivatives. And then furthermore, now I'm supposed to compute the coefficients of the Taylor polynomial. So it will be 1 divided by 0 factorial, which is 1. 1 divided by 1 factorial, which is 1. 1 divided by 2 factorial, which is frankly nothing but 1 over 2 factorial. So we cannot simplify that any further, but we do know that over here we'll have also 1 over n factorial and on. So that part is not going to simplify. The factorial has nowhere to go, but we know that now that we have this. This will give me Tn. These are the coefficients of my Taylor polynomial of degree n for the exponential function, and I can write it now easily. And in fact, just for practice, I will write in the form well, let me write it out first. So it will be 1. Remember the formula. So the coefficients. Well, let me actually maybe make our life slightly easier. I will point out what is that we have to multiply these coefficients by in order to produce the terms of my polynomial. So they are 1, 1. I'm sorry, x minus. Well, actually it's x, simply x squared, xn. Okay, now if I multiply these, I'll have 1 x, 1 over 2 factorial x squared. The next you can guess it's 1 over 3 factorial x cubed, and this is 1 over n factorial xn. Okay, and then that's pretty much it, because now I can just add these together, and at the bottom I'm going to have the nth degree Taylor polynomial. So it will be the sum of these. This is t sub n. The sum of these terms. Okay, I can now easily write Tn in the sigma notation. Remember the sigma notation that we have used a few times, and now it becomes more and more important because that's the only way to write sums in a compact fashion. So summation over k from 0 to n, and these are the coefficients. It will be 1 over k factorial, x minus a x, well, it's simply x. X kth power. So once again is the nth degree Taylor polynomial of f of x equal to e to the x at x equals 0. Okay, so very predictable writing. Where the summation comes from, you could I think you can derive more information from this if you are willing to write the formula in a recursive way. So because if this is Tn, then this will be Tn plus 1, the next one. So it will be 1 over n factorial, n plus 1 factorial, x n plus 1. Okay, so in other words, if you don't want one polynomial or one Taylor polynomial, you can have all of them in the recursive fashion. As you add one term at a time, you're moving down the table, down that column, and the last column, and you're getting more and more Taylor polynomials. So T naught of x is equal to, that's the starting point of the recursive definition, and it is 1, and then you go on and you say Tn plus 1 x is equal to Tn x plus 1 extra term. So that's what's happening to Taylor polynomials, or any polynomial. We add one term at a time. We're not starting from scratch. The next one is found from the previous one with one extra term here, so 1 over n plus 1 factorial x n plus 1. So that's the recursive way. It is all recursive. It's just that formula on the right, even though it's very compact, it kind of hides that point that the only way to compute such a sum is in a recursive fashion, one at a time. Okay, so that's the purely recursive definition of the Taylor, not the definition, but rather what we have derived about the Taylor polynomial of the exponential function. There is an illustration here of that here somewhere. Exponential function. Here it is. Okay, exponential function in green. Okay, this is T1. Oops, T1. So once again, the point of interest is here. Okay, so exponential function, it has an asymptote on the left. It goes to infinity fast on the right. 0 degrees 1 approximation. That's T0. This is T1. Okay, T2. So as you can see, how those red curves start to hug the graph close and closer over here in the middle. So it's the same point. And then straight line, then a parabola. Then look at it. It is this is T3. It is not a parabola anymore. You can see how skewed it is. Okay, and you can also see the errors. These are the errors of your approximation. And then it continues on. We're finding better and better approximation. Okay, so we'll continue next time.